And now the moment you've all been waiting for, we have the mean value theorem. Let f be a function that satisfies the following hypotheses, the same as before. F is continuous over the closed interval AB, f is differentiable on the open interval AB. Then there is a c such that, and then you have the derivative of c is equal to the slope of the points that you've chosen. And obviously for the second part, they just multiplied the b minus a to both sides, and you have the point slope formula. Okay, so what does this look like? So we have the mean value theorem, and let's use it on this equation to figure out what we're looking at. So if we have, it's x to the third minus x, a is equal to 0, b is equal to 2, then f prime of x is going to equal 3x minus 1, 3x squared. This is f of x. Using that formula, we have 2 minus 0. This is f of b minus f of a, f prime of c, b minus a. Okay, so this is going to equal the derivative, which is 3x. I'm sorry, since we're doing c here, we're plugging c in for x, c squared minus 1 times b minus a, which is 2 minus 0. Oh, and I'm sorry, I didn't get, this is not f of b. F of b is going to be 2 plugged into this, so f of b is equal to 2 squared minus 2, which is 6, minus f of a, which is 0 minus 0, so 0. All right, so that's better. So now we have 6 is equal to 3c squared minus 1 times 2, which is 6 is equal to 6c squared minus 2. We add the 2. 8 is equal to 6c squared divided by 6. C squared is equal to, that's 4 over 3 square root. And now c is equal to plus or minus the 2 over the square root of 3. Okay. Now, what is this? Well, this is the slope of the tangent line. And so what does this look like? Well, if we look at this slide, the red line represents the tangent and the, I'm sorry, it's not the slope, it's the point at which that tangent line is parallel to the secant line that passes through f of a and f of b. And so this is a very good theorem because now if you have something that's drawn like this, for instance, well, if this is your f of a and this is your f of b, right? You have this flat line. Well, that f prime of c being equal to 0 from Rolle's theorem, I mean, we could do Rolle's theorem again, right? We could use Rolle's theorem to do this, but now we can also predict that there will be a c value where that slope will also be equal to 0. And so we get these lines that are tangent to the secant line, or parallel to the secant line, and they're the tangents of the graph. And so it kind of, in a way, is like almost like a more improved version of the Rolle's theorem, because it gives us a little bit more. And so suppose that f of 0 is equal to negative 3, and f prime of x is less than or equal to 5. Well, let's use the formula right now. We've got f of a and b, so b minus f of a is equal to f prime of c times b minus a. And we have f of 0 being equal to negative 3. Okay, so we want to know f of 2. Well, we don't know what f of 2's value is, but we can put f of 2 there. Minus the value at f of a, which is f of 0. And we know that it's strictly less than 5 on this one. And so if we're going to do this, We can just kind of leave this alone right now. So we'll just say f prime of c and 2, oops, not equals, 2 minus 0, because we do know those values. And so we now have f of 2 minus f of 0 is going to be negative 3 is equal to 2 times f prime of c. Okay. And so if we want to keep solving, we have f of 2 plus 3 is equal to 2f prime of c. Okay. And then we subtract f of 2 is equal to 2f prime of c minus 3. Okay. But now we have to use the fact that f prime of c is less than or equal to 5. So this must strictly be less than or equal to 10, right? Because if you plug 5 into this thing, this is 10. And so we have 2 times 5 minus 3, which is 10 minus 3, which is 7. And so that's strictly f of 2 is less than or equal to 7. So, I mean, since it can be equal to, we would say that f of 2 is at most 7. And so we can kind of figure out the values of these functions and what they can equal to. And so then we've got this theorem: if f prime of x is equal to 0 for all x in the interval ab, then f is a constant on ab. That's kind of like the beginning part of Rolle's theorem from earlier. I guess I should prove this. Sorry, I thought there were 2 different slides, but we can prove this using the intermediate value theorem, or I'm sorry, the mean value theorem. So apply the mean value theorem. So let, what do we have? x1 and x2 exist in the interval AB, with x1 being less than x2, just so that we know they're different. Since f is differentiable, on AB, not AB, it's differentiable on AB, but it will be, and it must, sorry, AB, then this implies that it is also differentiable on x1, x2, and continuous. So using the mean value theorem, we have x1 is less than c is less than x2, and f of x2 minus f of x1 is equal to f prime of c x2 minus x1. Now, since f prime of c is equal to 0, right? Because that's part of our assumption from this. It said if that happens. Okay, so that's happening. F of x2 minus f of x1 is equal to 0, or f of x2 is equal to f of x1. And so, therefore, f has the same value at any two numbers x1 and x2 in AB. And so f is constant on AB. Okay, and so that would be how we'd prove that. And then there's a corollary. If f prime of x is equal to g prime of x, so two different functions that have the same derivatives over the interval, then f minus g is constant on AB. And that is that f of x is equal to g of x plus c, where c is a constant. And so another translation is if two functions f and g have the same derivatives for all x in an interval, then the two graphs are identical in shape and the vertical translation shifts of one another. And so that is it for this section. I hope this is kind of making sense. If it's not, we can talk about it during our Zoom meeting, and let me know what you guys think. Try to do the homework, see how you do. Thank you guys for watching.